All right, so this is recitation 4 on probability for CS155. And so today I'll be talking a bit about some of the fundamentals of probability. Tools are very important in machine learning. You will likely have seen some of them before, but I'm hoping that, especially given attendance, that this is an opportunity for you to ask questions about this and really make the most of it. Yeah, so I'll be covering things from sigma algebras to some Bayesian statistics ideas. And these are things that are pretty useful in machine learning, pretty important in the next couple of sets. But also, like, if you're interested in machine learning as a career, they might go on to define some pretty fundamental concepts. Okay, so, right. On the topic of like probability and why we need it, to motivate it, uncertainty is everywhere. You have a lot of data sets, you have noise, and sometimes learning is a hard challenge. So it's not always the best idea to have deterministic models. You need to have stochastic models. It's and to do this, we need probability. And probability asks questions like, over the long term, what can we expect of something? So and then, extrapolating from that to asking questions about right now, like statistical inference problems. So what is the chance that it will rain today? When will the next bus arrive? Will I go to recitation today? That one's computable, by the way. And the problem that we try to address in machine learning is, can we understand uncertainties and interact with the real world with these machine learning models, with these data sets? And the answer that we're trying for is yes. In practice, that's not always the case, but like stochastic models are making a lot of progress, and therefore it's quite essential that we learn how to deal with them. And probability theory is the way we mathematically study uncertainty, lay down the formalisms, and that's what I'll aim to do. So I'm not going to do everything rigorously, but the idea is that maybe I'll say a couple of things, and hopefully if you're interested in them, you will read about them later, but I'll try to be rigorous to some degree. So really most rigorous foundations of probability start with measured triples. So a measured triple is written as omega, a, and some measure. And I'll get to what this is in a second. So usually when you're talking about probability, there's a set of outcomes. For instance, let's say we're talking about our most recent example. Will someone go to class today? Either they will go to class, they will not go to class. Some people go to class, some people don't. And you have like, a finite set of outcomes. And sometimes, depending on what your question is, you can even have an infinite set of outcomes. So omega here is a set that denotes every outcome. Make sense? Okay. And then on top of that, we build the notion of a sigma algebra. So maybe I'll leave it. So omega is a sample space. And then A is the sigma algebra. And maybe I'll first see what it is and then motivate why it's important. And I think the best way to think about sigma algebras is a set of subsets of omega. So for instance, let's say that omega was the value that you get when you roll a dice. It can be 1, 2, 3, 4, 5, 6. And then A is a sigma algebra that contains a subset of all the sets of this. So there are a couple of sigma algebras, and we'll talk about them in a second. And I know I've said this like very unintuitively and not very rigorously, but in a second, I'm going to lay down the rules of what a sigma algebra is, and then we'll talk about it more. So we have a couple of rules for sigma algebras. So first thing, a sigma algebra is a set of sets. So one example of a possible sigma algebra would be the empty set and the full set. Are there any other possible examples you can think of? Just power set. Yeah, the power set, good. Okay, and turns out that these are actually the two sigma algebras. And so why is that? Because there are rules to being sigma algebra. The first rule is that any sigma algebra must contain the empty set. And so that's like the first rule. The second rule is that if there is some set in the sigma algebra, like if you say that B, the set, is in the sigma algebra A, then it is necessary that its complement, B complement, which is defined as everything in omega that is not in B, must also be in A. So what this is saying is that sigma algebras preserve complement operations. So that's the second thing here. And the third thing is sigma algebras preserve countable unions. So if you have some set of, or I guess if you have like a collection of sets, B1 all the way to Bn, where n is some finite number that is in omega, then the union of all of these sets, sorry, if these are in A, then the union of all of these sets must also be in A. So all that this is saying is that if you have some sets that are in your sigma algebra, then every possible union of them, as long as there are finitely many things that you're counting, must also be in the sigma algebra. So some things that we can see about this are, if the empty set is in the sigma algebra, and if the sigma algebra preserves complements, what else must be in the sigma algebra? Yes. So if the empty set is in A, then omega must also be in A. And another thing that we can see about this is, if the unions of a bunch of sets are in a sigma algebra, then is there anything that we can say about the complement of a bunch of sets? So for this one, you need to think about De Morgan's rule, which says that A union B complement is equal to A complement intersection B complement. So if a bunch of sets B1 to Bn are in the sigma algebra, and their union is in the sigma algebra, and we know that the complements of anything in the sigma algebra is in the sigma algebra, then the complement of A union B will always be in the sigma algebra. But that's the same thing as A complement intersection B complement. And we know from earlier that A complement and B complement are in the sigma algebra, so therefore the intersection must also be in the sigma algebra. So what this implies is that with De Morgan's rule, the intersection of a countably finite or countably infinite many sets are also in the sigma algebra. So those are the big rules. And there are two examples of sigma algebras, and these algebras are defined on a set. In this case, that's omega. And the two, like the trivial example of a sigma algebra is the empty set and everything, because you can see that it's preserved with the complement. So if omega is in the algebra, the only other rule that we must have is that its complement is in the algebra, and of course its union is omega, its intersection is the empty set, everything is preserved. And then of course you have the power set, and it's again like pretty easy to see that the power set is every single subset. So if something is in the sigma algebra, then everything else that's not that thing must also be in sigma algebra. Okay. So that was sigma algebra, and then finally you define measures. So measures are a way to quantify, to label, to put a value on these sigma algebras. So they're formally defined as functions from these sigma algebras to the real line. And one example of a measure is the probability measure that we will be looking at. But the few ground rules of measures are quite like logical. Mainly, the measure of the empty set must be, any ideas? 0. Does everyone concur? Yes. Okay. Yeah. And then the measure of anything must be strictly positive. Sorry, it must be strictly non-negative. So for anything for which the measure is defined on, that is for any sigma algebra, the measure of the sigma algebra must be greater than or equal to 0, because it does not make sense to assign a negative measure to anything. And then you similarly have this rule of countable additivity, that is like the measure of the union of disjoint sets. I guess like finitely many disjoint sets will just be the sum of the measures of each of those disjoint sets. So I'll maybe like paint a picture for why this is true. So I guess like just think about like, the classic Venn diagram, and you have some sets over here, B1, B2, B3, and you're just trying to compute the probability or the measure of the union of them. The measure of the union is just going to be the measure of this guy plus the measure of this guy plus the measure of this guy. Okay. And then I guess there are some other rules, but not for today. But I guess like the big one that I can think about is like if you have a small set over here, call it like U, then if you have a set that contains this set, called U prime, then the measure of U prime must be strictly larger than the measure of U. And you can actually prove that using some of the rules that I've stated here. But you can also read up on this more, and I'll provide some references at the end if you're interested in this. Okay, so the probability is a type of measure. It's a type of mu. It satisfies all of these rules. The probability of the empty set, the probability that nothing in your possible set of events occurs is 0. Every probability is strictly positive, well, sorry, strictly non-negative. And the probability of a union of disjoint events is a sum of the probability of each event. Does that make sense? So this when you apply mu equals the probability measure will be the classic example that you guys have seen from high school, probably. Yes. And so to be more rigorous, the probabilities of events are measured from 0 to 1. The probability of nothing happening is 0, probability of everything happening is 1, and you can define complements of this via 1 minus the probability of it happening. And you can also show this quite rigorously using measures. And the way to do that would be, well, so let A union A complement equal everything happening. These guys are disjoint sets. So the probability of A plus the probability of A complement must be equal to the probability of omega, which you know to be 1. And then subtracting probability of A complement on both sides gives you the result. So that's the measured theoretic way to show how to do this. Okay. So some classic examples. Suppose you're rolling a 6-sided die, then the probability, which is defined not on the element, but on sets, is just the probability of each of them occurring. In this case, for the singleton sets, it's just 1/6. And the probability of everything occurring is 1, or anything occurring from the sample space is 1. Okay. And similarly, you can define the probability of a union of events. And when there is some intersection, draw a classic Venn diagram. If there is some intersection, you measure the probability of each set, you subtract the probability of intersection. If there is no intersection, you can still do that, but the probability of intersection is 0. So it's just going to be the sum of the probabilities of each set. Does that make sense? Are there any questions? Okay, good. And then if you have like a more involved problem about finding the probability of a subset of the sigma of omega, but not quite the empty set, if they are disjoint events, the idea is that you can break them up into a finite set of disjoint events. In this case, the probability of rolling a 2, 4, 6 on a die is the probability of rolling a 2 plus rolling a 4 plus rolling a 6. Each of those are 1/6. That's a half. And you can also similarly do like more complicated notions, and the inclusion-exclusion principle, where you subtract the complement, allows you to do these like elementary operations here for probability. Okay. So let's talk about conditional probability. So this is more related to machine learning. So given two events, A and B, sometimes you might know one of them and you're curious about what the implications are on the other event. So to do this, we define, I guess, a more systematic way of doing this. So probability of A comma B is usually the shorthand for probability of A complement B. And it's just the probability that both events in the sigma algebra occur. Similarly, the probability of A, this is a vertical line, it means given B, is a probability of A if you know that B has occurred. And these are distributions. So the way you should think about it is A is a random variable, B is some random variable that has not been assigned a value. So one way to think about it is, let's say B is my height from 1 year ago, and A is my height from today. And I already know what B is. So given that my height was some value of B from 1 year ago, what is the probability that my height is some value today? So really, we're talking about the probability of A equals some value given B. And this is a probability distribution, which I'll talk about more in a bit. And you can, of course, relate joint and conditional probabilities using the conditioning formula, which is the probability of A given B is the probability of A intersection B divided by the probability of what you're doing here. And there's no real way to portray this using the Venn diagrams, but the idea is that you've now said that event B has happened. What's the probability that event A happens? And event A can happen outside the set or inside the set. But really what you're doing is you say that event B has happened is you're now restricting your sample space to omega. So in this new world, omega is now the set B1, and you're calculating the probability of something happening. That something could be, partially contained, not contained, and it could be contained. If it's not contained, it's going to be 0. If it is contained, it's going to be the probability of the intersection divided by the probability of everything. So you're kind of like renormalizing it. And that's like my intuitive way of thinking about it, but the formula is also an equally valid way to go. Questions? Yeah, so the probability of A given B is you're saying that event B has already happened. So what I said was that this particular set in omega B, and if I want to compute the probability of event A given B, well, so first thing is that I know that event B has happened. So if it's happened, you've restricted omega to events that can only happen inside B. So if event A happened to be disjoint from event event B, then the probability that they could both happen is 0. If it happened inside of B, then you want to find the probability of event A and B happening, which is this region over here, and then divided by the probability of B happening, because you're kind of renormalizing. So think about this as event A. So the probability of event A in this thing is just, the probability of A with respect to everything in this grid omega. But if B has happened, you then want to consider the probability with respect to the smaller grid of B. Does that make sense? Okay. Good. And of course, this is only valid if the probability of B is not equal to 0, and that must be true if B has already happened. Okay. And this allows you to do some pretty standard calculations. So here's one: consider a standard deck of cards. What is the probability that the first 2 cards drawn are both kings? So to do this, you can define some events. Event A, the first card drawn is a king. Event B, the second card drawn is a king. And you know that a standard deck of cards has 4 kings and 52 total cards. Are there any ideas on how we could compute this probability? Yes, right. So, usually when they say, what's the probability that both of these things happen, the probability of this and this happening, that's a clear allusion to the intersections of 2 events. So if you just do a bit of rearranging here, you'll see that the probability of A and B is the probability of A given B times the probability of B. And we know that event A is the event that the first card drawn was a king, and B, that the second card drawn is a king. So what can we say about that? Yes. Okay. So why can we do that? Why can we do that?
Well, it's like the switches just switch intersect.
Yeah. So the idea is that A and B is equal to B and A. So you can put these guys, and now you have something that's actually useful. So it's the probability of event A happening. Sorry. 4 out of 52. Okay, and then what's the probability of B given A? 3 out of 51. Because event B has been affected by A, so you're now living in the smaller universe where you have 51 cards and 3 kings. And you'll see that it is in fact that, so you multiply them, you get this probability computed. Okay, but we can also generalize this notion that I was talking about here, where you have this probability of A intersection B, and you can write it as the probability of B given A times probability of A. You can generalize it by adding more events, and that's what you do in a lot of machine learning and Bayesian statistics, where you're trying to compute the probability of A1 intersection A2 intersection all the way to AN. And the idea is that you can kind of recursively write this down as, well, what happens if I condition on A1 all the way to AN minus 1? So the idea is that you're saying, well, let's say that I happen to know what AN minus 1 over to A1 was. And then in this universe, I can compute the probability of AN given these things. So here, think about B as A1 intersection A2 all the way to AN minus 1. So the probability of A given B times the probability of B gives us the probability of A. Okay. So you have this guy. And then you're left with this residual. But then what's stopping you from doing the same thing again? Right? So you keep reapplying it. And then you get something that's like, the probability of all these events happening is the probability of my last event happening given my first couple of events happening, times the probability of my second last event happening, times the probability of the third last to the first event happening, times the probability, and you see how it goes. And you kind of write this very recursively, and that's what you do in a lot of dynamic programming with probability. And the fifth recitation on DP will expand on a lot of those ideas. Okay. So next, we say that two events, A and B, are independent if and only if the probability of A intersection B is equal to the probability of A times the probability of B. But is there anything we can say about that? Because we know from the conditioning formula that A intersection B is equal to the probability of B given A times the probability of A. So if you kind of combine those two things, you get the second formula, which is that two events A and B are independent if and only if the probability of A given B is equal to the probability of A. That is to say that your knowledge of B, if B has happened, if it has not happened, the probability of B remains fixed. So if B has happened, that doesn't change anything about your knowledge of that A. So here is an example. Let's say that I wanted to find the weather in a place like California, which is completely unpredictable. And it was raining. Well, it was sunny like a couple of days ago, and then it was rainy today. Was the fact that it was sunny a few days ago told you anything about it being rainy today? No, it's unpredictable. So that's meant to be slightly humorous, but I do believe that's actually not the case because there are some prediction systems. So maybe you can see where I was going, what I was going for. But yeah, so two events are independent if the knowledge of the event that has already occurred does not change your posterior probability about, event that you're interested in. Okay. And we've got another example here. Suppose you roll a 6-sided dice twice. What is the probability that you roll 1 both of those times? So let A be the event that you roll 1 in the first roll, B in the second. And those two events are independent because it's like a RNG. You pick a number from 1 to 6, and then you do so again. And these two events don't have anything in common with each other. So the probability of A intersection B is the probability of each of them, which is 1 over 36. So rolling a dice is an independent event. This, okay. And yes, as you said, A and B are like, I guess the operation A and B, or A intersection B, it's a commutative operation. So that gives you these two equations, and maybe I'll write it out. So you have the probability of A intersection B is equal to the probability of A complement B times probability of B. And then this is also the same thing, probability of B given A times the probability of A. And then you have this is equal to that, this is equal to this, therefore by transitivity, these two are equal. And that gives us Bayes' rule, which is the probability of A given B is equal to the probability of B given A times probability of A divided by probability of B. And this is probably like the single most important formula in probability machine learning, because you have like Bayesian inference and Bayesian models, generative processes, like all these like really big emerging tools in machine learning that rely on the idea of this kind of inference. So this is Bayes' theorem, and also there on the slides. Something to note is that sometimes this event B, the event that has already occurred, is sometimes intractable and most of the times like computationally difficult to calculate. So sometimes when you're doing calculations, it's fine to not be able to compute B, but there are some methods that do allow you to do that. And in this case, it's fine to just say that the probability of A given B is proportional to the probability of B given A times probability of A. Questions?
So we're assuming like it's kind of like a constant, it doesn't change too much.
Yeah, so B has already happened. So before that, it had a fixed probability. And the probability of the real number. Okay. And usually the problem in Bayesian statistics, now that we've like followed this continuation, is that we wish to examine some event A, which usually manifests in the form of data that depends on some event B, which is usually some parameters. And to do this, we have to define the Bayesian vocabulary. So the probability of A is supposed to be your prior information, which is the probability of A before we know anything about it, before we know anything about B. So let's say, for instance, I walk into the room and I want to find, and I randomly choose a person and I want to find their height. And I don't know anything about this room. I have no data. So the probability that I would expect of like, the average person's height would really depend on my prior beliefs on what the average height of a person is. And there's a distribution of that. But of course, this value is going to change if you then have a chance to examine the room. So the posterior probability is the probability of A after we've observed B. So maybe now that you've had a chance to look at the room, measure the heights of all the people, now you do know what the probability is of, choosing a person with this particular height. And I feel like that's like a pretty good example to think about things. Okay, but Bayesian statistics goes further than that, because it's not okay to just have your prior and posterior probabilities. You also need to define a way to get there. So to do that, we have something else called the likelihood function. And the likelihood function is defined as the likelihood of B given A is the probability of A given B. It's the posterior probability of when you switch the parameters. So what is the likelihood of B after observing A? And whereas the posterior probabilities, is the probability of A after we observe B. Questions? Okay, moving on. And then probability of B is what we call the evidence. And this is what I mentioned, which is the thing that was like, typically very hard to calculate, not impossible. There are some methods, usually like numerical estimations, like grid search methods that we do in EC 112. Yeah. So here's an example that uses the Bayesian, the Bayes formula, the Bayes rule, which is if a person has an allergy A and sneezing, event S, is observed with probability of S given A, which means that if a person sneezes, given that they have an allergy, is 0.8. What is the chance that a person has an allergy given that they are sneezing? So think about what's happening here, like big picture in terms of like what the data is. So you have these two events, sneezing, allergy, and you're trying to find out if a person has an allergy given that they're sneezing, which is a good question to ask. I'm like, well, if this person is coughing, what's the chance that they are infected? And that's a very important question to ask. But in reality, you don't know that. What you do know is the other way around. What's the probability that if a person has an allergy that they're going to sneeze? Because typically, if you know disease, you're going to know the symptoms. But if you know the symptoms, you don't necessarily know the disease. Okay, so in this case, you have all the parameters laid out. We've also been told that the probability of having an allergy is 0.001. A lot of people are immune. Assume that a good number of people sneeze, so probability of sneezing is 0.1. Given this, if someone has sneezed, what is the probability that they have an allergy? So Bayes rule kind of lays it out for us using the formula. So you can see that it's like pretty small given these parameters. I don't know if that's actually the case with real numbers, but that might be something fun to try out. Questions? Okay, moving on. So far we've been talking about some, I guess, like simple events of random variables with, outcomes like rolling a dice, picking cards. But usually we're sometimes interested in the probabilities of multiple events, multiple random variables. So to get there, we need to define some notation. So we talk about random variables as results from experiments usually. And the measure theoretically to talk about it is if you have some event in your sigma algebra omega, which is in big omega, or rather omega which is in A, then a random variable is just a result of randomly drawing something from omega, capital omega. But the measure theoretically looks at random variables as functions of these results that you draw out from omega from omega to the real numbers. So that puts random variables as a mapping of events to the real line. So, and then one way to think about these distributions of these random variables is the probability that a random variable takes on a particular value, a little x, is the probability that the random variable takes a value. So this is actually an abused notation for two reasons. Guesses? There's a easy answer. The easy answer is that we're using x twice. And then there's a measure theoretic answer, which is that x is really a function. So what's the probability that a function takes on a value? It's kind of like a big question to ask unless you know the input of the function is. And the reason this is the notation is because we need to say that x is a function of omega. Right, questions? So now, armed with this new map, let's talk about the dice roll again. What's the probability that the random variable x, which denotes the result of this drawing of rolling a dice, so drawing randomly from 1 to 6, what is the probability of the random variable taking on any of the values in omega? It's 1/6. For a biased coin, which is an important model that we study, if you bias the probability of having a 1 to p and 0 to 1 minus p, biased coin and with a fair coin, p is equal to half. Right, and now we can also define something else called the cumulative distribution function. So typically you have some probability distribution function, which is just if I have some value of x, what is the probability that big X is equal to little x? And I'm just like laying it out graphically here. For instance, let's say that it was we have a coin, and let's say tails was a -1 and heads was a +1, and this is just a half. The probability of having a tails is equal to the probability of having a heads is equal to a half. And you can think about more complex distributions, like the height of class of people, which is like you can assume to be kind of like normal distribution, something like this. You have a lot of people who are short, a lot of people who are you have a lot of people who are like average height, a few people that are very short, people that are very tall, and then you have a distribution. And on this distribution, you can find the cumulative distribution function, which is for a particular value of x. What is the probability that if I choose an event in omega, that its probability is less than that? So the probability that x is less than this particular value, little x, is defined as a cumulative distribution function, and that's a function on little x. And similar to the probability measure, something that we have properties of the cumulative distribution function are that they are bounded between 0 and 1. Why is that the case? Right, because the probability, because capital F1 is the probability of everything that has happened. That is the probability of omega, which you define to be 1. Similarly, what happens when we talk about x equals 0? The empty set, which has n equals 0. Good. And then we have properties that f of x is monotonically increasing, which means if you keep going to the very end, everything has happened. It's 1 at the limit. If you keep going to the other end, it's 0, nothing's happened. Questions? Okay. Moving on. Yeah, so you have discrete random variables, which are variables that can only take on a finite number of different values or accountably infinite. These random variables have a probability mass function, which just measures the probability that a random variable from this distribution reaches a particular value. And then, like all probability distributions, the probability of everything must be equal to 1. So the sum of the distribution must be equal to 1 as well. Okay. So classic example, you're flipping 2 coins. Let x be the random variable that equals the number of heads. And then you can have the event that there are 0 heads, 1 heads, and 2 heads. If there are 0 heads, it's the probability that you have tails and tails. That's a fourth. The probability that you have 1 heads is tails and heads, heads and tails. It's a half, and then 2 heads is a fourth and a fourth. Sorry, a half and a half, so fourth. Okay. And then for continuous random variables, you now get to use some methods from analysis and calculus particularly to define the probability measures, because for continuous random variables, the probability is not defined on a particular number. Does anyone see why? Right, there are an infinite number of things. So the measure theoretic way of dealing with this instead defines continuous random variables on Borel sets and then does this thing called the Lebesgue measure on it. And the Lebesgue measure kind of measures the width of intervals. So we're not going to talk about that here, but the idea is that you're kind of taking an integral between 2 points, and the area under your curve is the probability. Questions? Okay. So classic example of the uniform distribution between 0 to A. You pick a random variable uniformly randomly. It can be its value can be anything from 0 to A. So what's the probability that it's anything within that interval? It's going to be 1 over A. What's the probability that there's anything outside that interval? Sorry? 0, yes. What's the cumulative distribution function? It's going to be x over A because it's a constant slope. So if you take the integral, you're just having an x over A plus some normalization term. In this case, that's 0. Okay. And then you can define marginal distributions. And the big idea that I like to think about this is how it relates to the law of total probability. So let's say that I wanted to measure the probability of some event. Actually, yeah, okay. So let's say that you have a bigger set omega, and this is some event B, and you're interested in computing the probability of B. And one way to do it is to break up omega into partitions. Call this like omega 1, omega 2, 3. And I claimed that the probability of event B happening is the probability of B and omega 1 plus the probability of B and omega 2 plus the probability of B and omega 3 and 4 and 5, 6, which is nothing in 7. You see that here. The idea is that in trying to measure a set, you rather measure its joint intersections, and then you keep the sum over everything. And you can kind of like generalize this notion to finding the probability of some event x as you're just summing over for all possible ways you can split apart your sample space omega with the probability of x given y. Sorry, x and y. But the condition here is that every y that you choose over here, these guys must all be disjoint. Because if it were no disjoint, let's say that you have like something like this over here, you'd be double counting, and we don't want that to happen. Does it make sense? Okay, so that's the law of total probability. And saying it more formally, the probability of A is equal to the sum over all finite splits of omega of the probability of A and B. That's the same thing as if we use our Bayesian probability rule, the sum of B and omega of probability of A given B times the probability of B. And this is also a really important result because it tells you that if you know the posteriors, the posterior events, or if you just know the likelihood of something if something else has occurred, you can then use it to calculate the overarching event that we're interested in. Does it make sense? And then similarly, this idea has a continuous analog, which is the marginal distribution is now, instead of summing over all these y's, you're taking the limit as these boxes are really small, so it's now the integral. So you're just integrating out everything in y's, negative infinity, and then the marginal distribution for the small variables here. So
when you say B. In this case, B would be like actual would be like Y would be like the total.
Yeah, so in this case, X would be equal to B, and the Y's would be this maker.
Yeah, and then when you do the opposite, Y would equal that makes it. Sorry. Okay.
Yeah. Make sense? And then similarly, if you have a grid of discrete, events, common example is if you want to find the probability of x1, you just take the sum of x1 across all possible values y1. And similar idea for the integral. Yes, and then after that, you define the expectation of a random variable. You've probably seen this before. The sum of x and the probability that x, the random variable, takes on the value x. You can define its integral in the continuum limit of the same way. Properties of the expectation, it's linear. So expectation of a constant times a random variable is a constant times the expectation of the random variable. The expectation of the sum of two random variables is the sum of the expectations of each of them. Okay. And some classic examples. And I think we're running a bit low on time, so maybe I'll skip over this example. I'll post up these slides so you can see it later. You can further define the variance of a random variable as the measure of spread of the values the variables take on. For machine learning, variance is typically bad. Well, it depends on what you're talking about. If you're talking about the performance of your model, you typically want good performance guarantees. That means you want it to perform well with high probability with a low variance, so it's always performing well. So the variance of a random variable is kind of defined as a measure of spread relative to its mean, and is defined as the thing on the top, expectation of x minus expectation of x squared bracket. And you'll see that if you just do all the math, that it's equal to the expectation of x squared minus expectation of x whole squared. So it's the square. I guess you can think about it as like the mean of the squares minus the square of the means. But variance is not linear. If you have a constant that you add onto the thing, the variance does not change because you're moving everything by the same amount. But if you multiply it by something, then by the formula, it contributes a square to your term. And if you have two random variables and you add them, the variance does not depend on each of them, but also on their interactions. So you have to consider the covariance matrix. So the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x and y. And you can derive that as well from the equation above. The covariance is defined as, so think about the variance of x as the covariance of x comma x. So if you plug in y equals x here, the covariance would be the variance. But if you're interested in the variance between two random variables, you replace one of the squares with the analog term with the y's. So it's the expectation of x minus expectation of x times y minus expectation of y. Yeah, and example that we'll skip. You have some discrete distributions, the Bernoulli distribution, which is if I flip a biased coin that lands with heads with probability p, and x is 1 for heads and 0 for tails, the distribution is what's the probability that the Bernoulli random variable is going to equal a particular x. And for this case, it's going to be, for a couple of iterations, it's going to be heads with some probability p, x times, and then tails 1 minus x number of times. The probability of tails is 1 minus p, has this p. The mean of a Bernoulli distribution is 1 times the probability plus 0 times the probability if it doesn't happen. That's just the probability p. You can then look at a binomial distribution, which is the sum of a bunch of Bernoullis. So the probability that takes on something is just going to be the number of ways the Bernoulli can happen. So you just take on your probability for the Bernoulli and you tack on and choose x, which is a number of ways the event could happen. And then the expectation of x is by the linearity of expectations, the number of variables n, times the expectation of each of them, which is p, so np. Then you have the geometric distribution, which is how many times can you flip a biased coin until you land heads with probability P. So what that's saying is that you're going to keep flipping it. You're going to keep getting tails. And then all of a sudden you're going to get a heads. And then the expectation of that event is 1 over P. And there's some, I think there's a game online called like Beat the Odds, like a trading game for people interested in quant, which just asks you to like do a bunch of geometric distribution calculations, and it's pretty fun, would recommend. Yes. Okay, so going on, the Poisson distribution, which is if you have an event that occurs at a particular rate, for example, receiving letters, and the average number of letters received per day is lambda, and x is the number of letters received in a given day. The probability that big X is equal to little x can be computed via lambda to the x times e to the negative lambda divided by x factorial, where the mean is given by lambda. And then you have uniform distributions, which maybe I'll skip for now, but the idea is that I think we actually might have talked about it earlier, so I'll definitely skip that for now. And then of course you have the normal distribution, and this is like the really important one. It's just tells you that you have some distribution that has a high concentration around the mean and low concentration around the extremities, and is given by a distribution that's some function of the exponential of the means and of the standard deviation, which is the variance, which is the square root of the variance. Yeah. Okay, and then there are two things involving these random variables that are pretty important to talk about. The first of them is a law of large numbers. If you have x1 to xn, it's a set of independent and identically distributed, which means that you're picking them up with the same sampling process. And each of these random variables has an expectation of mu. Then all that the law of large numbers tells you is that if you just take many of these random variables and you average them, you're going to approach mu if your number of samples converges to infinity. So if I wanted to find the average height of people in a room, or maybe of people on Earth, I could start by measuring the average height of people in this room, and then people in another room, and keep. What I'm saying is that as my sample size increases, I'm going to get there to the mean. Does it make sense? Yeah. Good. And then the central limit theorem kind of quantifies the rate at which your variables converge to the mean, and it tells you that if your variables are IID with mean, mu, and finite variance sigma, sigma squared, then your sample average is going to be approximately normal with mean mu and variance sigma square over n as a function of the number of samples you take. And as n approaches to infinity, you get exactly a Gaussian or a normal distribution. Yeah, and so this is a pretty important assumption. And sometimes it's used very misleadingly, especially in Stat 6. So be careful. Okay. And then the last thing that I'd talk about would be maximum likelihood estimation, which is suppose that you have a parameterized distribution, probability of x given theta, where theta is unknown, and you have an IID set of samples, x1 to xn. The question is, how can we estimate theta? So we use the Bayes theorem, which says that the probability of theta given x is proportional to the probability of x given theta times the probability of theta. And then upon this, you define two quantities. The first is your mean your mean a posteriori estimation. So it's the posterior estimation of the mean of, so it's defined as the theta that maximizes the probability of theta given x. So what is the most likely event, the most likely value that theta can take given x? In other words, if my height was 1 point, I don't really know, like 5, 6, 2 years ago, what is the most likely value that my height is today? That's the mean posterior estimate. And then the MLE is the value that we're interested in, and that's defined as the maximum likelihood estimator. And that's the theta that maximizes the probability of x given theta. And there are some important ways to do this, especially computationally, that are also important for the SAT, which is that it's sometimes hard to calculate this argmax of f of x given theta like it's hard to calculate the MLE. So it's easier to apply the log function to it. And while we're doing that, we might as well tack on a negative, because our goal in machine learning is usually to find the minimum of something. And log happens to be a convex function. And from set 3, we know that all convex functions have a global minimum. There's a reason we introduced a problem. Okay, so the argmax of f of x given theta is the negative log of f of x given theta. It's the same optimization problem that we're trying to solve, except now instead of a max, you have a min. And then you can see a problem like this. So suppose you toss a biased coin n times, record the number of heads. What is the probability that lands heads on a given coin flip, given that you know its history? So in this case, you're just trying to find p hat, which is the maximizer of the probability of k given p. And expanding it out using the binomial distribution, you get the first 2 lines. Well, the first line, and then Enchi's k is irrelevant with respect to p, so you might as well get rid of it. And then from there, you apply the negative log. And that simplifies things out a lot. So, and because you can, you get like a neater expression, and then taking the derivative allows you to, and then setting it to 0 gives you your global minimum. But I was going to say that this is actually quite important for numerical simulations, because floating point errors are a real thing. Doing negative log is quite important for this. Yeah. And another problem that you've seen before in log regression is, you have some data set S, which is just a bunch of observations, X, Y. X is the data, Y is the label. And you want to model it using the log regression formula, which is the probability of Y given X WB is defined as the sigmoid function of sorts. And then the question is, can we use MLE to find W and B? And the answer is yes, using this method, because the probability is, so you have like, a bunch of events. The probability of all of them happening is the product of the probability of each of them happening. That's the independence assumption. And then using our log trick, the argmax becomes a negative argmin of the log. And that's what's happening here. And from there, you'll see that formula actually becomes like really easy to compute. And it has a gradient. So you can then do log regression pretty easily on this. So that's pretty much all I wanted to say today. I referenced some good notes on this topic, and I'll put up some more on Piazza if you're interested. But that's all I had for today. If there are questions, stick around. Yes. Stop share.